Well, thank you everyone for joining us today for our virtual analytics day. Hopefully our next one will be in person. But I have the distinct pleasure of introducing a former student, Alfredo Escriba. Alfredo is Chief Technology Officer and Executive Board Member at CAPSH TrafficCom Ag. He has 20 years experience in transportation and related fields such as tolling and autonomous and connected vehicles. He holds a master's degree in irrigation and drainage systems, rural engineering, an MBA, and a master's of analytics from Texas A&M class of 2017. So a jack of many trades. His capstone project was recognized as honorable mention for the Roland Acra overall best capstone project, and was also recognized as a rising star in analytics for pioneering in his industry. So welcome, Alfredo. We look forward to hearing what you have to speak about today.
Thank you very much, Mira. Thank you for having me. It's a real honor to be back here. As Mira was saying, I started my journey in data analytics here in this house and with this program. And that was my eye-opening and deep dive. It was a great couple of years dealing with the masters. I travel a lot. I remember doing classes and exams from hotels, offices, different places from Australia, Austria, Spain. So it was pretty intensive, but it was really worth it. So for those of you that might be thinking on doing it or not, I highly recommend it. So here I am, a few years later, as the head of technology and product management in CAPS. I will give you a little bit of a glance of who is CAPS. My role now, I would say that is less technical of what I would like. So I'm in the intersection of technology and products and business. And I would say that probably one of the things that I regret with that is that I don't have physical time today to do my own things in data analytics, which I enjoyed very much in the past, but now I need to manage things that are doing that for the company. So with that, who is CAPS? To put a little bit of the context on what I will do during my presentation, CAPS is the #1 tolling company today in the industry worldwide. For those of you that are on the East Coast, we are the company that is behind EasyPass. So all the transponders that you have on the windshield of your vehicle, and those kind of weird gantries that you have on the roads while you are driving that are used for you to pay tolls, this is us. Or when you go into Austin, all the tolls that are around the city of Austin is systems and technology that we provide. We have another activity in the company, which is traffic management. And what we do in traffic management is the systems that are behind whatever changes the variable message signs that are alerting you of accident. We are the people behind as well the technology that makes the traffic lights change from red to green. And in today's world, we are as well one of the companies that is putting that information into the connected vehicles, which is one of the use cases that I will explain on this presentation. To give you a glance, for instance, the whole state of Georgia is managed in all the highways, so it's managed by our technology, or UK as well is using our technology to manage their roads with some things where we are doing some predictive analytics into what traffic might be, etc., which are some of the topics that I will be covering. So what I will do in the presentation, I'm gonna get you a little bit on the context of transportation, which is probably something that some of you might not be familiar with. So I will take some minutes on that. Then I will go through some of the use cases, variety of them that we are applying today that might be less visible of the sounding board today of autonomous vehicles. And then I will give you a little bit of out of experience, some tips or things that really matter when you get into data analytics on this, and probably apply to many other industries on what is the real day today, which has sometimes some roadblocks or some difficulties that especially for us who have that profile of data scientists and we really like to play with the data, et cetera, sometimes make us get a little bit frustrated. So with that, let me give you a very quick view on transportation and why all this matters to transportation. So to put the context, who doesn't struggle today with a traffic jam, congestion, or air quality problems? I would say everybody is becoming even more and more frequent. The trend of population moving into cities all over the world continues happening and will continue happening. Metropolitan areas are going to continue growing. Trips are going to grow as well. At least that is what the projections are telling us. And even after pandemic, we can see that the number of vehicles and the miles traveled per year in the US, as an example, as of today has almost recovered. We are probably, depending on the location, 5 or 10% down, but it's pretty much as it was before the pandemic. Public transport is a different story, but people driving their own car has almost fully recovered. A lot of people, 73% of people is commuting to metropolitan areas, and 73% of them spend more than 90 minutes sitting on a car, wasting their time. That's the reality. And investments continues being limited, and they will continue being limited. So we need to contribute from technology to enable things that cannot be paid anymore by building more infrastructure. And then one topic, again, that is more and more important in today's world, which is the energy consumption and the emissions associated to transportation. 30% of the emissions that are being produced today come from transportation. So on all this context, when we talk about what are some of the challenges that we have in transportation, until recently, and I would say probably 3 to 5 years ago, the transportation sector has been very static. Static in the sense that many of the algorithms and technology that we were applying did not evolve significantly for many, many years. We still have a segment where we don't have enough data in many cases. The old ways of getting that data that were based on sensors, like installing a magnetic loop on the road or using microwaves or something like that, which are still the mostly used and existing in the current installations. They provide some information, then provide some data, but it's not what we would like to have as traffic engineers and data scientists. And that obviously affects what we can do in traffic management. Traffic management in many cases still is not adaptive, meaning that the traffic management systems do not react or do not act proactively or even reactively to what are the real traffic conditions or what are the traffic conditions that we should expect. They run in many cases still based on fixed times, meaning that, for instance, the traffic lights change from red to green based on some predefined patterns, depending on the day of the week and the time of the day, but they don't react to the real traffic conditions. We continue finding many silos when you go into a Department of Transportation, you have too many departments. Each one of them have their own data. The data is different, et cetera, et cetera. So this is one of the real painful points that we have when we try to put all this into practice. And as I was saying, technology now is catching up. We have seen a rapid and big change in the last, again, 3 to 5 years, probably more 3 years, that now is coming finally where we are starting to apply some of these things that I'm going to be talking about today. And finally, connected vehicle. Until now, the only way of connecting a traffic management center with you as a driver was these variable message signs that were telling you or alerting you if you were going to be having some accident 2 miles down the road, et cetera, et cetera. And rather than applications like Waze, which is not yet really connected to the traffic management center, it's partially, but it's not really connected, that disconnection still exists and will be solved through connected vehicle, which as well is things that is moving relatively quick in the industry. The point of view of our citizens, no surprise, people want cleaner and more livable cities. People doesn't want to be sitting on a car wasting 90 minutes per day. People want to have access to transportation in a much easier way. They want to have information to know what is the best option to commute tomorrow or today or this morning. Do I take my car or I get on a bus or I get on the tube? What should I do? People want all this to be easy and convenient. Safety is very important, and I will show you later some numbers that I don't know if they will surprise you or not, but are significant numbers in terms of fatalities that we have in the US, and people want to have multiple options. So what are the enablers that we are having in the transportation space? Data. Okay, now data is changing. Now we start to have other ways of getting data that is very important for how we manage this. We start not to depend only on that magnetic loop or microwave detector, which is one single point of information. We start having other sources that I will explain later. Technology is helping the computing capacity, what we can do with artificial intelligence, data analytics, machine learning, what is coming through the mobile phones, et cetera, et cetera. Connected vehicle, fundamental on all the equation of transportation, and is really a change. The automotive industry, believe it or not, until recently was not on the table of transportation. We were managing the roads for vehicles, but the vehicles manufacturers were never sitting with us on that equation when we were talking with the Department of Transportation or not. Now, thanks again to connected vehicle, that ecosystem is changing, and now they are sitting with us on the same table discussing how we can solve some of these problems. The consciousness that I was mentioning before, and yes, the pressure for what is going on in transportation, et cetera, and what are the emissions or how transportation is affecting to climate change needs to be more transparent and better. So this is kind of the context of what is going on in transportation today. The public authorities that are dealing with transportation, they have two main missions. They need to manage the roads on a safety environment because they need to give us an infrastructure where we can drive safely. And it needs to be sustainable. And sustainable, you can put on that basket climate change, emissions, accessibility to transportation, or dealing with traffic jams, which at the end of the day reduce the quality of life of all of us. So in transportation, like in any, I would say, any other, let's say, engineering problem of this nature, I'm just going to go a little bit through the cycle, just kind of a little bit of a refresher. The first step, you need to collect the data, which is a challenge. It's not an easy task. For those of you that have gone already through your capstone project, or might get started your capstone project, you will be surprised on how much time you will need to spend at the very beginning dealing with data until you have a data set that now you can start using and building your model. So this is not different, and this is the reality of the day-to-day. The data needs to be enriched. You need to pull out different sources of data, put all of them together. You need to do inference, etc. Because in many cases, the data that you get from only one source is not enough and is not good enough. After that, you need to start driving decisions. Now you start processing the data, you start running your algorithms, etc., etc. Now you have an output, and then you need to decide what to do, because in some cases you might have different options and different alternatives. You can do a prediction of what traffic is going to be, which is great, is fantastic, but then you need to decide what you are going to be doing on the field and what is the best course of action. And this is where as well simulation, as Patty was mentioning on the NVIDIA presentation that she did, etc., come into the picture as well. So you need to act. You can do a prediction. If you don't do anything with that prediction, and that is common sense, sometimes do not happen. In transportation, it's very, very important that once you know what you are going to be acting on, you need to give that information, because we try to influence to some extent behavior, and there is two ways of managing behavior, either with incentives, positive or negative. Either you pay at all, or I give you an incentive if you do what I'm recommending as a traffic authority, or I give you the information so you can be making some better informed decisions. So it's very important that in transportation we communicate once we have decided what is the course of action on all this life cycle. Obviously, later on we need to analyze. We need to see how that did go, if it was effective or not, and then seek for ways of improving. We need to prepare for the future, because the next time as well is going to happen, and we need to take the lessons learned of how we manage on this initial cycle. So with that, I'm going to move. This is kind of to picture a little bit the complexity of the ecosystem. You have a lot of stakeholders on the left, navigation applications, data sources, companies that are emerging today, along connected vehicle, etc. You have fleets, you have car manufacturers, you have telecom companies, etc., etc. You have the vehicles, you have the road users, you have the road infrastructure owner, and then on all these yellow boxes, then we need to put all that together as part of our technology stack and produce something that can be used on a traffic management center or on a tolling highway. So the ecosystem is pretty complex. There is many stakeholders, and it's getting more and more complex. So with this high-level view of what is the context of transportation, now I'm going to start illustrating a few of the use cases on where we are using the data analytics technologies that exist today in the market, and how are we doing. The picture that you have in the screen is one of these weird gantries that you see today in the highways as you drive. They can be pretty complex. As you see, there is a lot of devices hanging there. You have readers that are reading the transponder or the tag that you have in the windshield of your vehicle. You have cameras. You might have laser curtains that are separating vehicles and helping us to discriminate what is the category of the vehicle, because we need to know if it is a truck with a trailer, an 8-wheeler, or if it is a motorcycle, because depending on that, we need to charge you. And all this is something that we need to do in an automatic way without human intervention, of minimizing the human intervention. Because think, in some of these highways, or in cases where we do nationwide systems, we might be processing 2 million transactions per day, 5 million transactions per day in the bigger systems. it's rare that you have a system where you are processing less than 500,000 transactions. So imagine all this if you would need to do it process manually. So the picture that I sent is some countries that were a little bit of the past, where you could see some laser detectors and more complexity of what is today. So what data analytics has helped us to do is to reduce part of that complexity, because a lot of that we can do it today through video, using machine learning in video, using deep learning. And that allows us to do the classification of the vehicle, the identification, at the same time reading the license plate, etc., which are all data points that we need to get. So because of that, we have been able to reduce that complexity. So today, in many cases, you can simplify that and have only one box here, the one that reads TRX. That still is the reader. That is based on radio frequency, that is connecting directly with the transponder that you have on the windshield. And all the rest of the pieces and the information that we need is processed by this VDX sensor. That sensor is first identifying the vehicle, is giving us the category. If it is a truck with a trailer, we can even read and identify how many axles the vehicle has, because based on that, you pay more or you pay less. And at the same time, with the same equipment, we can read the license plate to do a double verification with your transponder. If you are who you are saying you are, if the transponder is on the right vehicle or not, or even identify those cases where there is someone that got on the road without having a transponder, in which case we will need to send a ticket later. So all this happens in seconds, because you are driving behind that gantry at 70 miles per hour. You could drive if you want at 100 miles, don't do it, but you could do it if you want, because the technology is ready to process that in milliseconds. So this is kind of one of the things we do with these video stereoscopic cameras that we have, and applying machine learning, we are able to get these volumetric profiles where, as you can see, we can identify if a truck has a trailer or not, if either is small or big. We can identify if it is a motorcycle, and so on and so forth. At the same time, I was saying that we need to take as well a picture of the license plate that we process. Again, this is one of the typical applications that all of you have learned, that was kind of the earliest starts of machine learning using neural networks to process the license plate. Now, something that sounds, oh, well, yeah, that's kind of easy. Well, I can tell you, we have installations here in the US where we need to process 300 different types of license plates. Some of them have colors. Some of them have other type of characters. Some of them have other type of messages written on the license plate. Up to 300 different license plates. Something that looks like relatively easy can become very, very complex. And we could not do it if we would not have behind some very powerful algorithms that are able to process all those different license plates in an accurate manner. And we don't get to 100% recognition. So there is always a percentage of license plates that need to be processed manually. We have not got in the industry to a point where we can process 100% automatically, which is one of the costs that you have when you are running one of these installations and you're running a highway. There is some manual processing. That technology still is not there to give you full automation. We need as well automatically to hide, when we take a license plate from the front, we need to hide if there were people on board because of privacy reasons. We cannot give this picture to anybody identifying that there were 2 people or 3 people on that vehicle for privacy reasons to get you protected. So this is as well done in an automatic way. We need to directly hide and put this black box in the middle of the picture while we preserve the reading of the license plate. One of the other interesting and cool things that we are doing, this is a little bit of a digital twin that we use for our engineering teams. So I'm going to run the video. So what you see here on the upper left corner is a recording of a real highway. So we record this, we apply our deep learning algorithms, translate that into digital, and then with some other gaming tools, what we do here is, you see on the right corner, on the upper right corner, that we are changing kind of the angle. You see that now it changed the angle on how we will be seeing the vehicles. So we use this to help our engineering teams to pre-engineer on the lab what would be the configuration of that gantry that I showed before, where the cameras would be installed based on the visuals that we can get and the different angles, etc. And if we can simplify as well the installation and the infrastructure that needs to go into the field. So this saves us a lot of time, because when the teams go into the field, we know if we need to install a gantry, or in some cases, we can simply install a pool that minimizes the cost of all the installation. So another example on how we are using this type of technologies. With this, I finalized, I finalized the tolling piece. It was super fast. Obviously, we do other things in terms of seeing how users are using the road, etc., etc. Some profiles in some B2C businesses that we have launched, but I will not enter into that, it will be too long. And then I'm going to move now to the traffic. This video is one of the things that we are doing as well with one company where we are shareholders. We don't own the whole company. It's a startup, but it's pretty cool what we are doing with them. So let me play the video.
Audi has been leading the race toward a piloted driving future since we tested the first autonomous TTS at the Bonneville Salt Flats in 2009. Since then, our piloted cars have climbed legendary mountains, beaten back track times, and even driven from San Francisco to Las Vegas. But a truly autonomous future depends on a vehicle's ability to communicate and know the world around it. As the industry leader in mobile connectivity solutions, we are adding yet another to our long list of firsts. Introducing traffic light information. City traffic lights today are often controlled by a central traffic control system. Audi has collaborated with providers to receive this data in select cities. When an equipped Audi comes into a monitored traffic light zone, it requests the light phase information from Audi data servers. If at a red light, the system displays the time until the light turns green. A better informed driver means a less stressed driver. Traffic light information is the first step to an incredibly connected smart city. Eventually, city grids will not just send, but will also receive data from road traffic, getting real-time updates when and where surges are taking place to adjust traffic light times. Imagine, no more waiting at a red light while green cross lanes are empty. The city could then understand where bottlenecks have formed in real time and adjust traffic light signals to optimize traffic flow. And this is just the beginning. Audi is pioneering a future where cars aren't just sensing their surroundings, but communicating with the city and the other cars on the road. The first steps are here with traffic light information, available only from Audi as part of an Audi Connect Prime subscription.
All right, so, well, first, I have nothing to do with Audi. I'm not, I don't work for them, but we are working with them. And so we are the providers for this functionality that you see now on the screen to Audi. You can buy any Audi today in North America having this functionality enabled, which tells you basically when the traffic light is going to change from red to green or from green to red. You would argue, well, but that is information that is known on the traffic management center, et cetera, et cetera. Yeah, to some extent, because the device that manages the traffic light on the field is pretty autonomous. and it makes their own decisions. And there is latency in communicating that to a traffic management center, et cetera, et cetera. And today, the deployment of connected vehicle is so-so. So what we do here is we do a prediction based on historical data, patterns, even we emulate some of the systems to be able to tell the drivers what the traffic light is gonna do as soon as you get into the range of that traffic light. That, the first and simple application is comfort. You can drive more relaxed. You can avoid speed up or brake suddenly, or the typical thing that we all do when you when you drive through an arterial full of signals is that you always guess if you are going to make it on time to the next signal, or if the next signal is going to open to green when you get there. And we all tend kind of to speed up, etc., and then brake. All right, if you know what the traffic light is going to do, you can modulate your speed significantly better. And that has many consequences. The first consequence is that one of the big problems that you have in traffic is the stop and go, because of the harmonic that it produces upstream is what ends creating more traffic jams of what it could be. So if everybody could drive in a smoother way, traffic flow would be significantly better. We can give you from the traffic management center as well the recommended speed that you should be driving, so you avoid this stop and go, et cetera, et cetera. And if everybody follows that, and even we can create with a few vehicles inserted in a platoon harmonization effect, so the others kind of start accommodating as well, we can improve significantly the traffic flow. We can reduce emissions. Some studies that we have done with some universities in Canada with real experiments on the field say that we can reduce fuel consumption 20%, and we can reduce emissions 20% simply by doing this. And think as well in electric vehicles. In electric vehicles, you could extend significantly the life of the battery if you avoid stop and go, acceleration and deceleration. So if you are able to run the vehicle in a much smoother way, the lifetime of the battery is significantly extended. And all this is based on the prediction that we built from when the traffic lights are going to change. There is even one safety application, which is mainly meant for trucks. With a truck, we want heavy truck that needs a lot of space to stop. By using this same principle, what we are able to do is tell them and make decisions in real time when the truck gets on the dilemma zone. The dilemma zone is, I'm going to make it to the green, or I'm going to need to stop. So we are able either to manage that better, making that the truck has enough time to stop, or even if we see that the truck is not going to stop, we can extend the green, so we create a safer situation. This is, for instance, an application that we are going to be during this year. We are going to be piloting in one city in Texas. Actually, I cannot say where, but we have already executed a contract with the government to test this, and it's going to be meant specifically for trucks, thinking on this safety application. Now let's go into more kind of the day-to-day of a traffic management center and some of the things where we as well can create value and do better operations. We can do performance measurements on how things are going for planning or for detecting things and how the things are working and reacting. We can build origin and destiny matrices and give information about travel times as well to know patterns, what is going to happen. We can do some predictive analytics. And then we have many other things as well, kind of on the backlog of things that we are exploring to see if we can get them in production. So let me go through a few examples on this. This is another application where we use video a lot. Remember that at the beginning, I told you that the traditional method that exists in most of the places today is that I have a detector, which is a single one. I don't know if you see my mouse, but probably situated 100 meters or 100 yards upstream of the stop line. That'll give me only one single point of information. The rest, what is in between that single point and what is in the until the stop line, I need to infer, I need to guess. And traffic engineers have been very good at creating some algorithms based on experience on these things, but they were to some extent guessing because they don't really know what is in between, how many vehicles in reality, what type of vehicles, etc., etc. So by using video, we are starting completely to change the landscape because the dream of a traffic engineer that is managing an intersection is to know how long is the queue of vehicles that they have on that intersection. So here, the good thing is that we can use with the technology that we have developed, companies even like NVIDIA can provide to us or through their ecosystem, we can now know exactly what type of vehicles we have there, what is the length, and how many do we have. These numbers down here, 8, 9, 5, 5, is telling me how many vehicles I have on that queue. So my traffic engineer can now estimate that significantly better. Yeah, now he's not guessing, now he knows. That allows him to know or to do things like extending the green. Regulating better this intersection, because I might have in too many cycles of the traffic light, I might have a very long queue that I'm not even able just to evacuate when I give the green. So I need to articulate and change that split of times on the cycle of an intersection. Or I can detect as well an incident like this one, where we have a car stopped in the shoulder, that can trigger automatically an alarm to the control center. And then someone in the control center can start doing something. So this is kind of a screen with different boards and things that we are doing. Let me focus, for instance, on origin and destiny matrices. Origin and destiny matrices here is something that we develop mainly for cities. And we use, I will talk about the data that we use, but what that allows the traffic engineer is to know how people is going to move during the day, from where to where, and what routes they are going to follow. You can imagine that that is of high interest to the traffic engineer, because with that, he knows what is going to happen this afternoon, what is going to happen tomorrow, and he can start preparing the plans in case that he has some abnormal situations that he will not be able to deal with. But also, this is very important for planners. What has changed in the industry on this as an example? Until now, most of the origin and destiny studies were based on surveys. Basically, people going out there and asking you, where are you going? From where are you going? And what means of transportation are you going to be using? Today, thanks to data analytics, we can start doing this in an automatic way and even give you the what is going to happen tomorrow morning. How we do that, what data we do collect. We have one city where we are using Wi-Fi. So the city got Wi-Fi in the whole city. And we read the Wi-Fi of your mobile phone. In other cases, we use the cameras that are installed for traffic surveillance or even security cameras. And through license plate as well, we can know how many vehicles and from where they are moving, doing some tracking. Don't worry, confidentiality is one of the norms. It's zero leak requirement that needs to be taken very rigorously, but that gives us very, very powerful insights on how people is moving in cities. Is when you use this type of data, for instance, from smartphones, is not that easy, because one of the things that we need to deal with is we don't know, when you have a bus, you probably have 30 people within that bus that is giving you a signal, hey, I'm here, and the same with GPS locations. So we need to figure out and create algorithms to discriminate that, because that counts as one vehicle, yes, a bus, but it's one vehicle. Or you might have 4 people on the same car that has their iPhone activated and is radiating as well as 4 people. And we need to infer that and filter and determine that is one vehicle. So it's can be relatively tricky. Anomalies. What we try to detect with anomalies is not congestion, but abnormal congestion or situations that are happening. That needs to be coming in the form of alerts so we can act. So again, an anomaly could be because a car crash, could be a lane closure that we were not aware of, that sometimes happens, can be because of weather, or can be simply because one sensor that we had on the road is not working properly. And then we start seeing weird profiles like the one on the screen. So the picture on the left is not an anomaly. This is normal congestion that we have in New York. The one on the right is an anomaly because we should not have these rates. So by comparing that, it tells us, hey, you have a problem on this piece of road where maybe you don't have a sensor, but I'm seeing something weird upstream where I did have a sensor. That is what we detect with anomalies. And you can see on this picture, on the down part of it, on the lower part of it, you can see all these reds. The accident on this case was created on Blackburn, but we saw the effect obviously upstream, and we see the effect on the 3 segments that are above upstream or where the accident happened and how that has propagated. Accidents or crashes. This was started through my capstone project. You see kind of what I was saying, the accidents, even the miles have decreased or recovered. Accidents have gone back to levels of 2016 and even above. And I can tell you that 2021 is not better than 2020. Still, we don't know in the community why that has happened, but we have gone 5 or 6 years back into dealing with crashes and casualties and fatalities because of crashes. And the problem is not only the number of fatalities, which is 40,000 people per year in the US, is as well the severe injured people that is the result of it. And that number, the severe injury, continues growing. So we have reduced the fatalities to some extent or stabilized, but the number of injured people continues going up. So what we can do for the traffic authorities on this regard, we can give them a prediction of what is the likelihood that there will be an accident on any given road at any given moment. So we can produce a map like this with the hot spots, which are these red bubbles. And we can do this during the different hours of the day. So this is just one system that is now operating in the city of Madrid on the Beltway. This is very easy conditions, 2 a.m. to 3 a.m., low traffic, no risk. 3 a.m. to 4 a.m., we start seeing some reds, which is a little bit weird. This will require some investigation because it does not sound like something normal, but maybe some conditions on that day, there were maybe an event there or something like that. The risk is going up as you start getting into rush hour until you get to here. We have most of it already with some potential problems of potential accidents until you get to peak hour, where almost everything is in red. So what can a traffic authority do once they have this prediction? Well, they can first put their cameras looking into this, because their cameras are monitoring the whole road, but they don't know exactly where they should be looking into. And the cameras that they have on the field are the eyes of the traffic operator on the traffic center, so they can do that. If they have any way of harmonizing speed through variable speed signs, they can use that, because instead of letting people continue driving at 90 kilometers per hour or 60 miles per hour, they can get that down probably to a more safety speed like 40, where they can reduce the risk of accidents. Or they can have emergency crews and service patrol located strategically in the close to the spots where those accidents have the higher likelihood of happening. So there are things that can be done to mitigate the effects and do some prevention of this, not only reaction with the service patrol, but also prevention with reducing the speeds, etc. or simply signaling, hey, watch out, in this section, the risk of accidents is high. We can do prediction as well. This one, some of you I know, I did the same at the beginning. Oh, I can do this, getting a little bit technical with time series. Time series is not the most effective. So what we ended doing here was creating our own patented algorithm that is based on clustering. So we cluster profiles, and then we are able just to assign the conditions of the day to the best cluster, and we do the prediction based on clusters because there are patterns in traffic at the end of the day. So what we need to find is what is the pattern that applies to the conditions that we are foreseeing today. Finally, some performance measurements, which are on the direction of, again, providing information for decision making. They can be more operational, they can be more historical, for planners or to help longer term effects or actions, and then analytical performance, which are more kind of oriented to prediction. So an example of this, for instance, here we can give travel times to the operator on the traffic management center to say where he's having, maybe this would be an anomaly, maybe not a big one because it's not going down brutally, but he should know that this one that is red, the travel time that he's having now is off limit, because in free flow conditions, he should be in 5 minutes from this segment to this segment. In normal conditions that apply now, he should be in 7 minutes 25, and he is a little bit above now. So that gives him a trigger to look what is going on there. Do I have something weird, or is something that I need to look into? We can build historical maps as well on, for instance, a heat map on speeds or traffic flow or other parameters that the traffic engineer wants to see where they are having problems. For instance, one of the things that we do with traffic lights, by analyzing what is going on the traffic light, crossing the data of the traffic light with vehicle data coming from floating car data that I will explain what that is, we can infer if that intersection, the pattern and the cycle that is running is properly adapted or not to the real traffic conditions. Floating car data is data that is coming basically from GPSs, from vehicles, either from smartphones or today from connected vehicle. So it's individual GPS points that when you put all that together, it gives you very good insights on how traffic is acting. Obviously, you can imagine what is behind, because we might be processing, I mean, any company that is today using that is processing billion of data points per day that they need to assign to one location on the map. With that, I finalize kind of the use cases, and then I will move now into kind of some things that I wanted to highlight for you on the day-to-day practice of data analytics. 3 obstacles. Data islands. When we work with our customers, we find too many silos, we find scattered systems, etc., etc. And one source, as I was saying before, normally is not enough. So we need to figure out how to get different sources and deal with those islands that we find in the real world. Resistance to change. We have many traffic engineers that say, hey, but I know the patterns. I've been doing this for 20 years, until you show them the pattern, and then they get surprised and say, wow, I was not aware of this. Yes. So, but that resistance always happens. And budget, obviously, is a topic that we all should have into consideration. Key aspects, this is more kind of problem management, but obviously applies to everything that we are discussing here. The first thing, you need to see the big picture. Doing data analytics for doing data analytics, or creating an algorithm for that, without the context on how it is going to be used and what problem it solves, don't head into that path, because it will not be used. So you need always to think, what problem am I solving and how that is going to be used. Let me give you 2 examples. I can give you a prediction of traffic, but the next question that always comes is, now I know that the train is coming, what do I do? So you need to provide the tools to close the loop into how you translate that into action, solving the problem. So the prediction alone is not enough. And the other one, for instance, when you do a prediction in crosses, you can get super high accurate into the true positives, but that tends to produce a lot of false positives as well. And if you give a traffic operator too many false positives, what is going to happen the next day is that they are going to switch on the application because it creates too much noise and distraction for them. So you need to find a balance and always keep that into consideration once you design your applications and your solutions for real life problems. Automation, essential. Again, I mentioned to you, we might be processing millions of transactions per day. So you need technology behind to do it. It's impossible to do it manually. And partners. I was mentioning, funny enough, this in the NVIDIA presentation from Patty this morning, because one of the problems, and I deal with that with my teams on a daily basis, especially when we talk with engineers and software engineers and data scientists, is that we have fun inventing things and creating things. We have a lot of fun. That is what we like. But if I could give you a recommendation, avoid inventing the wheel. Today, the good news is the ecosystem of technology out there is huge. Many things are already invented. Use those partners that exist out there. Use the ecosystem. Finally, availability of data and access to data is not an easy cake. It's probably one of the most difficult things. If we would have access to the data, we could enable a lot of these things, but unfortunately, that is one of the shortcomings that we have on the industry, the data quality and the coverage as well. And then in our specific case, it's very, very important that we are able to geolocalize that information into a map, which is a piece of road, which also has a lot of challenges and requires a lot of automation and technology behind, so we can make use of it. I have some other slides that I'm not going to enter into it, so at least we can dedicate some minutes to Q&A.